Applications of exponential functions. In an effort to control vegetation overgrowth, 100 rabbits are released in an isolated area free of predators. After 1 year, it is estimated that the rabbit population has increased to 500. Assuming exponential population growth, what will be the population after another 6 months? Round to the nearest rabbit. Okay, so we have our function here, and the p of t, this part represents the final number, the p sub 0 represents the original number, a is some constant, and the constant of growth, by the way, and t is your time in years. So what we need to do first is calculate what this constant of growth is before we can calculate how many rabbits will be there after another 6 months. So we know that after 1 year, 100 increased to 500. So we'll have 500 is equal to 100 a to the 1. This is the original amount, this is the final amount, this is the time. So that's really just 500 equals 100a. Divide both sides by 100. So a is equal to 5. Now we can use this in this formula to calculate how many will be there after another 6 months. So what will the time be in another 6 months? The time will actually be that 1 year plus those 6 months. So the time is going to be 1.5 years. So now we just plug this into our calculator. 100 times 5 to the 1.5, and we get approximately 1,118 rabbits. That's pretty crazy, isn't it? The compound interest formula looks like this one. Again, A of t represents the amount in an account after this number of years, after t years. P represents your principal or the original amount. R is your interest rate in decimal form. N represents the number of times per year that interest is added. So that's called how many times per year it is compounded. Here's another N, and the T again represents how many years. Terry invests $3,560 in a savings account, earning 2.3% annual interest compounded daily. What is the value of Terry's investment after 4 years? Well, it looks like he's going to start with this amount. So your P is going to be 3,560. And it looks like the interest rate is 2.3% or 0.023. It's compounded daily, so N is going to be 365 days a year. So we want to know what's the value. We're looking for A of t after 4 years, so t is going to be 4. So now all we need to do is plug all of this information into the formula. So A of 4 is equal to the principal times 1 plus the rate over n all to the n times t. So plugging this in the calculator is the trickiest part. Let's see if we can talk through this one. What I do is 0.023 divided by 365. I have my number in my calculator. Now I add 1 to that. The number is still in my calculator. I raise it to the 365 times 4. I still have a number in my calculator. Now times 3560. And I get $3,903.05. If you ever start estimating these numbers along the way, then your answer will be slightly off to really, really bad off. So be really careful whenever you use your calculator on these problems. 18 months after depositing $1,200 in a semi-annually compounded savings account, Carol checks the balance and finds the account has $1,310.15. Carol can't quite remember what the annual interest rate for the account is supposed to be, but sees that another bank is advertising a rate of 3.5% for new accounts. Should Carol close out the existing account or open a new one elsewhere? Well, we need to help Carol calculate her interest rate. So we use the formula A of t equals P times 1 plus R over N, all to the nt, where we know the A of t is the final amount, the P is the principal or the original amount, the interest rate we don't know, it's compounded semi-annually, that means 2 times a year, and this was after 18 months, so the time will be 1.5 years. Okay, so the very first thing we want to do is divide both sides by this 1,200. That'll make these reduce to 1. So I get 1310.15 divided by 1,200. I have a number in my calculator and I'm going to store it. There's a little button just above the on button on a graphing calculator. It's called stow. So I'm going to store that, stow, and then I'm going to push the alpha button and then the math button. So what I did was just store that number in the letter A. So right now I have A is equal to 1 plus R over 2 to the 2 times 1.5, which is 3. Well, to get rid of this 3, I need to take the cube root of both sides. Well, the cube root is the same thing as to the power of 1/3. So while this number is in my calculator, I'm going to raise it to the 1/3 power. Now I have another number. I'm going to store that in alpha matrix. That would be my B. So now I have B is equal to 1 plus R over 2. That's because these cancel each other out. Now that B is in my calculator, I'm going to subtract 1 from it. So I do minus 1 equals, and I have some number, I will store that one in alpha C. So I have C equals R over 2. Now to get rid of this 2, I multiply both sides by 2, and I find out that R is approximately 0.059412 blah 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 blah. So her interest rate is about 5.9%. So should she change banks? The new one is offering 3.5%. So no, she should not change banks. Continuous compounding formula. If P dollars are invested for T years in a continuously compounded account with an annual interest rate of R, the accumulation is A of T, which equals PE to the RT. So again, A represents the final amount in the account, P is the principal, R is the rate, T is the time in years. E is a button on your calculator. It's some constant. So looking at this problem, Jessie has the option of investing $5,600 in a continuously compounded account earning 3.6% annual interest for 2.5 years. What will Jessie's accumulation be at the end? So we're actually looking for A again. And the time is 2.5 years. The principal is what he's starting with, which is 5,600. E to the R, which is 0.036, T, which is time, or 2.5 years. Punch this straight into your calculator. 5,600 times second, where is E? That's going to be your ln button. So second ln, and then 0.036 times 2.5. Close parentheses equals, and you end up with 6127.38 once it's rounded. So this is how much would be in his account at the end of 2.5 years.